Marius, go ahead.
Okay, so good afternoon, good evening, and good morning, everyone, based on wherever you are. My name is Ankur Srivastava, and I'm joined with my very esteemed colleagues, Professor Kushanfar and Professor Curry. I just realized I'm the only one who doesn't have a last name that starts with a K among the speakers. So that's an interesting fact that I just observed. Anyway, so welcome you all for our to our tutorial. And we have a very exciting set of 3 talks which delve into the details of hardware security, which touches upon many things, including AI hardware and AI algorithms, given the timeliness and significance of this topic. There are 3 talks. I'll start the presentation on our tutorial on a concept called as design obfuscation, which has gained substantial significance in the last few years. But for some reason, the architecture community really hasn't delved that much into details of this problem. And our motivation is that in the general context for general processors or general microarchitectures, and even specific to AI hardware, how can design obfuscation be investigated or reinvestigated, and what are the agendas? And what is this problem really, and why is it so important? So I'll be starting with that talk. And I'm Ankur Srivastava. I'm a professor of electrical and computer engineering at the University of Maryland. Professor Kushanfar will go next. Is that okay, Farinaz? Will follow me, and her talk will be about machines for robust machine learning and machine learning for robust machines. And Professor Kushanfar is a professor of, and also she leads the Machine Learning Institute at the University of California in San Diego. And then I'm also joined with Professor Ramesh Curry, who will be talking about high-level approaches to hardware security. And he is a professor at NYU. So without much further ado, I'm going to start my presentation, and I'll do that by sharing my screen. Just some housekeeping. If you have any questions, please post them in the chat box. What we'll do is each of us will probably talk for about 50 minutes, 45, 50 minutes. And if need be, if there are some urgent questions, the speakers can answer those questions in real time, or we'll have a 10-minute Q&A session after each talk, and then we'll switch to the next one. And in the end, if there is time, then we'll answer some of the questions that are remaining. And then you can always reach out to us if you have any further questions. So on that note, I'm going to share my screen, which is right here. Let me do this. Okay, great. So welcome you all. So I'll be talking about design obfuscation. So what is hardware security? Hardware security in itself as a field has gained substantial attention in the last 2 decades, a decade and a half. And specifically, the problem of hardware security deals with questioning the assumption that the hardware is secure, or hardware can be assumed to be a root of trust. And this comes from the fact that hardware itself is built on a very distributed, a very non-secure supply chain. A lot of work has gone into asking the question, what happens when you have fabs which are not trusted, which are building your designs, and fab really has all the ability to steal your design, to put Trojans in your design. But increasingly, the realm of hardware security is being expanded to incorporate designers as well. So you have designers who are also working in a distributed setting. You have design teams which are spread out all across the globe. And can the designers be trusted? And then you also have this issue of side channels, which deals with attacking the hardware in field when the hardware is in use to steal the information that is being executed on the hardware. So it's a very rich field now in terms of ideas, in terms of problem formulations and stuff like that. And also it is a very strong, small but strong community of professors and students and industry as well. So I'll be talking about circuit design obfuscation or design obfuscation, which deals with the presumption that the foundry is untrusted. So the designer itself is trusted, and the designer comes up with the design. They come up with the GDS2 file, and they send this design to the fab, and now the fab knows exactly what you are building. And now the fab can do anything with it. It can overproduce and sell your chips or sell your designs to competitors. And if there are nation-state attackers involved, then they can know, especially in the context of military hardware, exactly what type of systems you're building, and that's a problem. So design obfuscation is an approach where you try to hide the design details from the fab itself. So the fab builds what needs to be built, but the fab doesn't know exactly what you're building, either in terms of functionality or in terms of its timing and power signature and what have you. So how do we do that, and what type of challenges are out there? There are a lot of papers in the logic community, in the EDA community, not so many in the architecture community, and our hope is that this tutorial will motivate some of you to start looking at those types of questions in micro, HPC, ISCA, those types of venues as well. So logic locking is an approach to address this problem. So what logic locking is that during design time, the designer locks the combinational portion of the design using additional gates called as key gates. And for example, you have this little design over here, which is the black portions is the original design, but then you have added these additional key gates. And the functionality of Y1 and Y2 now become a function not just of the inputs, but also what the key values here are. So when you expose this design to the fab, because the fab doesn't have the correct key values, it doesn't know exactly what the functionality you're building. And just from the structure, it cannot decipher what the correct key value or what the correct functionality is. So there has been a lot of work which tries to find what are the right type of key constructions, key gate constructions. Some of them have used XOR gates, XNOR gates. Some have used muxes, lookup tables. There's a whole gamut of work out there which comes up with the right constructions for locking the functionality of the designs. But then there have also been many attacks, but one of the most prolific attacks on logic locking is called as the SAT-based attack. It came out around in 2015. And what the SAT attack does is that it assumes the attacker, which in this case is a fab, has access to two pieces of information. One information is, of course, the design, which they know, with protected design, right, with all the locking key constructions and all that embedded. So they have this netlist of the design, but they can also go to the open market and buy an unlocked chip, right? So an unlocked chip will be a chip in which there is an on-chip memory, which is protected, which is a tamper-proof memory, which has the correct key. And that correct key is going to be feeding the key gates. And this is going to be the correct functionally correct hardware. Now, because the key itself is stored in tamper-proof memory, it cannot really be probed. So they don't know exactly, they cannot just read the key values from this working system, but they can stimulate this activated hardware to get some input-output behavior. Now, of course, in the worst case, they can sample the entire input space, which is 2 to the n possibilities. And if n is, let's say, 1,000,000, then that is an exhaustive brute force way to search the correct key value is not a feasible approach. So what the SAT attack does is that it is a very smart way of taking the protected netlist combined with information that can be probed from or queried from this oracle to figure out what the correct key value is. And it's a very, very powerful attack from the experiments. And what it basically does is that iteratively it reduces, using optimization theoretic combinatorial optimization concepts, to reduce the space of unknown in the correct in the key space to find the correct key. So what it really does is that you have this protected design, right? And this protected design is then formulated into a SAT formula. And the purpose of the SAT formula is this, that it tries to find an input X such that there exist two key combinations, let's say K1 and K2, such that the output, the simulated output from the netlist are different. And then it goes to the oracle, which is our working system, and queries for this specific input X what the correct output is. Now, either one of, so both the keys that you found here from the SAT formula cannot be correct, right? So either one of them is correct or neither of them is correct, right? So by querying the system, it can tell that for that specific input X, which of the keys are incorrect, right? And that information is then fed back into this SAT formula, and then you solve the SAT formula again to find another input for which there exist two keys, which result in two separate outputs. And then you go back to the oracle, and then you query the oracle again, and then you keep doing this till the SAT formula does not give you an input X for which there exist two keys with separate outputs. And at that point, you have found the correct key. So this is the SAT attack. And the SAT attack is actually a very, very powerful attack. And one would think that, you know, in the worst case, of course, the total number of times you go to the oracle can be very many. But practically, we have found that for most, at least at the time, about 2015, most of the solutions for protecting designs in this way were hopelessly underserving the objective of obfuscation under this attack. So then, you know, the question became that can we come up with new constructions which are resilient to the SAT attack? And our work and work by another professor who's, you know, Ramesh's former student, J.V. Rajendran, came up with the first SAT resilient construction. Our construction was called AntiSat. JV's construction was called SARLock. And basically, what they did was that they came up with a very unique way of locking. And, you know, I have, you know, this little figure over here to illustrate that. I'm not really going to go into the mathematical details here, but there's a lot of math here. But if you lock the construction in this way, then you can actually prove that the total number of times you'll need to go to the oracle will be at least 2 to the n, where n is the total number of keys that you have, provably. So what that meant was that the SAT attack became infeasible for large enough key values. So if your key is 256, at least you'll need to go to the oracle 2 to the 256 times, and that's just impractical. So that, and here is a little you know, illustration of the fact that the theory matches the practice. So the red was the non-SAT resilient design obfuscation constructions, where, so as you increase the key size on the x-axis, the CPU time was basically flat. So the increasing the key size was really not helping at all. But for our anti-SAT construction, as you increase the key size, the complexity of SAT attack became exponential. So that spawned a lot of research in SAT resilient logic locking constructions, and one of the state-of-the-art approaches, and I'm not going to summarize everything here, but I'm just giving you a little tidbit that one of the state-of-the-arts in logic locking is called as SFLL, or stripped functionality logic locking, which builds upon some of these ideas that I just presented. Now, our group also investigated other ways of doing logic obfuscation, which is to use 2.5D or 3D IC technology. So what you can do is, let's say, some layers of the 3D IC can be manufactured in an older technology node, but a trusted technology node, and the others could be manufactured in whatever TSMC Global Foundries, because those are not trusted fabs anymore. And then the question becomes, how do you partition your design into trusted versus untrusted layers? And how do you make sure that there's no information leakage from the untrusted layers about what is being made in the trusted layers? So it's a design partitioning question and an information leakage minimization question. But so there has been a lot of work, theoretical as well as illustrative work on logic obfuscation. A lot of companies are incorporating this type of technology in chips. You know, both Ramesh, I, and Farinaz have been recruited by companies to help them put this technology on new tape outs. But fundamentally, logic obfuscation, at least the way it's been investigated so far, has the following limitation, and that limitation has nothing to do with our conceptual investigation. It is a little more fundamental in nature. So there's a theorem which says that you can actually show that fundamentally there's a trade-off between SAT attack resilience and wrong key corruptibility. So what does that mean, right? So let's say you have a chip and that you've locked with a key, the functionality of which you've locked it with a key. Your objective is that when the key is wrong, the functionality should be really, really wrong, right? Because if the functionality is not really all that incorrect, then what's the point locking anyway, right? On the other hand, you would also want your locking constructions to be resilient to the SAT attack. Now, you cannot achieve both. And there is an entire theory why you cannot achieve both. It comes from Boolean algebra and all that, which I'm not going to go into the details of. But for example, what is illustrated here for SFLL, which is the state of the art, it is that if you increase the error rate for the wrong key at a functional module level, so module level error rate for wrong keys, which you want to be high, and probability of finding the correct key. So if you, the probability of, if you choose a locking construction, any locking construction, which has high wrong key error rate, then you cannot escape a high probability of finding the key using the SAT attack. So what you'd like now, you want both. You want to be resilient to the SAT attack, but you also want your module level error rate to be high. So how do we achieve that? So one direction that our group pursued was to construct a new type of locking called a strong AntiSat. And strong AntiSat is based on the presumption that not every input is equally important, right? So if you look at, for example, the MNIST benchmark or the ISL BRC benchmark, and if you look at the parameter distribution, most of the parameters, at least for the MNIST benchmark, are around 0, right? Which means those are the typical values that the neurons will end up processing, which means if you end up, so when you lock, what you really do is when a certain input happens to your chip, then the functionality for the corresponding output is corrupted. So that's why we say input locking, right? Locking for certain inputs to your functional modules. So instead of locking, for example, this parameter, which is never really going to happen, and therefore the error rate will be 0 because that input never happens in your chip, right? You would rather lock those inputs which are more popular, right? And then using this, so there is this notion of critical minterms or critical inputs, and you would prefer to guide your locking mechanisms more towards those inputs which are more relevant. So in that sense, the strong anti-SAT construction identifies and assigns higher corruptibility for only a very small number of critical minterms that result in low module level error, therefore high SAT resilience, right? But high application level error, because what you're locking and what you're corrupting are very relevant inputs, right? So this was a construction that we proposed last year, and it was published in a journal. And then we, in the same spirit, we asked another question, which is conventional logic locking was about a certain input happens, right? And if the key is wrong, then for that specific input, the output is going to be incorrect, right? So that construction basically happens at the truth table level, right? So you have a truth table for, let's say, your adder or your controller, or what have you, right? And then you want to modify that into something else, which depends upon the key values. But that is entirely time independent, right? So we asked the question that, can we expand the scope of logic locking to include temporality, which means that instead of just locking when a certain input happens, or corrupting when a certain input happens, at that moment, can we actually lock or corrupt sequences of inputs, right? So let's say the trace, so that's why we call it the trace-based logic locking. So what we want to do is if a certain sequence of inputs happen, then and only then we lock. So if the sequence of inputs is I0, I1, I2, and if I0 happens independently, or I2 happens independently, or I0 followed by I2 happens, but then it becomes I4 after that, then there is no corruption, right? But only when you have I0, I1, I2 happening in a sequence, only then do you lock. And I'm not going to go into the details of this construction, but this is what this construction looked like. So you have a little finite state machine that basically counts the sequence and then sends a signal which says, okay, corrupt now, when that input happens. So what that does is that at the module level, the corruptibility is still very low, right? Because you are really, at any given time, you're really not corrupting anything. But the specific trace that you lock has a very high corruptibility for the application, right? So this type of locking, therefore, still results in high application level corruptibility, as well as high resilience to SAT. So these types of discussions are important. And here is some data. I don't want to go into all this data again, but as you can see over here, so if you look at the blue plot, as the trace length is increased, the probability of finding a key goes down exponentially. So it goes from, let's say, maybe 50% or 30% all the way to 0.01 or something like that, right? Very quickly, if you increase the trace length from 1 to 3. And the application level corruptibility is still very, very high. So if you look at, for trace level locking, if you have a processor that has an adder that is locked using TLL, the parsec benchmark fail rate is almost 100% for all these different parsec benchmarks. So this sort of highlights the importance and significance of these new directions in design obfuscation. But all this motivates us to talk to you, which is the architecture community, to see if there is a question we can ask at the architecture level, right? So far, much of the work as far as design obfuscation is concerned, and Farinaz has done some excellent work at protecting finite state machines, and there has been work, some of which that Ramesh will present, which deal with high-level decisions as far as design obfuscation is concerned, but specifically at the architecture level, because the design of architectures follow a very specific design method. Is there a question that we can ask at the architecture level on how to lock or how to protect processors at this level, right, or at the microarchitecture level? So the main idea is to explore the effectiveness of locking at the architecture level. Now the question is, why would we want to do things at the architecture level? Why should we not just do things at the lower functional module level, and that's all that you need to do? Why do we need to bring this architectural view into things? So to ask that question, we developed a tool called as Obfusgem, which you can download from GitHub, and we released it last year. So it's a comprehensive logic locking simulator based on Gem 5. And what it does is it performs cycle accurate simulations for gate level IC designs secured with any logic locking technique. So what you can do is you can decide from a library of different logic locking solutions. You can decide which to choose and which to apply to which architectural module, right? Branch predictor, this, that, anything. And then we can emulate, we can of course simulate the impact of that locking solution at the application level using the Obfusgem simulator. So it gives you a quantified impact of locking on applications run on locked IC netlist. So this is kind of the whole framework for the Obfusgem simulator. My student calls it a pioneering architectural system that allows us to evaluate any module level locking construction. I would not use the word pioneering, but certainly the impact of Obfusgem can be quite substantial. So using this simulator, now we can ask this question: that do we need an architectural view on things? Let me just. things? Yeah. Do we need an architectural view on things? And here is a snapshot on some of the results. So what we did was that we logged various modules using, I think we used SFLL here, of different severities, right? So let's say we chose to log, let's say, the adder, right? The adder is black, but there are multiple blacks here. So I think this is probably corresponding to the adder, and then we logged two architectures. One was based on the x86 core, the other was the ARM core, and the SFLL locking was applied at different severities, which means that at different module level error rates, right? So we found that when the module level, and then we evaluated for different severities of the SFLL locking for, let's say, the adder or the multiplier or any of these different modules, what was the fail rate for the parsec benchmarks? And this is averaged across all the parsec benchmarks, but we have data for the individual benchmarks too. And this showed that most of the locking was in this red zone, which is that when the failure rate was high for the wrong keys, which you want, you want the applications to fail when the key was wrong, right? For most of these cases, and for most of these locking constructions, you were in this red zone, which was not resilient to SAT attacks. So if you look at the x-axis corresponds to the probability of finding the key in a certain number of iterations, and you can see that in this red zone, the probability is quite high, but the error rate is high too. So if you want the probability of finding the key to be low, you had to kind of give up on the fail rate or the error rate at the application level. So just a module level view on things is not sufficient, right? So we need to kind of bring architectural smartness into locking processors, and that is why our hope is that in the years to come, some of you would get interested in asking this question. Use OpusGem, collaborate with us, and the whole 9 yards. Okay. So we did try to make things a little more architectural aware, a little more predictive about what's the best thing to do so that the impact on the application is maximum. And then so there were a whole bunch of different modules that we locked with different approaches. What I'm showing here is the functional units with 4 functional units with some smart scheduling. Smart scheduling was when certain inputs that are more likely to be corrupted are given to locked. So you don't want to lock everything because there is an overhead for locking as well, right? So let's say you're locking only 2 functional units. So there is going to be a smart scheduler which will put more corruptible inputs to these locked modules because you want to have the impact if the key is wrong on the application level. So that's an architectural level decision, not so much a module level decision, right? So when you did something like this, then we came more in the wide zone. So the parsec benchmark fail rate became quite high, even in a zone when you had SAT resilient locking. So this architectural view or the application level view or system level view is important as far as logic obfuscation is concerned. And my hope is that the years to come we'll see more papers in the ISCA, Micro, and HPCA type conferences on this problem. Okay. So moving forward, we continued to look at other ways of doing design obfuscation. So far we have talked almost exclusively about design obfuscation or functional or Boolean functional obfuscation. Boolean function obfuscation, but that's not the only game in town. There can be other parameters to lock as well. So one parameter that you can lock is the timing signature of your chip, right? So it is much easier for you to come up with the functionally correct design than to come up with the timing correct design, right? So if the main intellectual property or a significant aspect of the intellectual property in your design is its timing construction, or how things are synchronized and how things are made timing correct, then instead of just limiting yourself on functional locking or protecting the functionality, maybe we should also protect the timing signature, or we should do both, right? So in order to do that, we came up with this notion called as delay locking in a DAC paper in 2017. And that had a very simple construction like this. So we had what is called as a tunable delay buffer, which had a key controlled heavy capacitive load. So what this did was that when the key was 1, then this capacitance was reflected here. When the key was 0, then this capacitance was not reflected here. So the timing of this path became a function of the key, right? Now, anyone who's done chip design will tell you that there are 2 types of timing constraints that you have. One is the longest path constraint, which is something that we talk mostly about, right? But the other is this race path constraint, where the longest path constraint tell you that you don't want paths to be longer than a certain clock frequency, and you want that to be as small as possible because you want to clock your processors or chips at the highest possible clock frequency that you can. But you also have this notion of shortest path constraint or fastest path constraint in order to avoid race conditions. So you have both, right? So what you want to do now is you want to very smartly incorporate these tunable delay buffers in your design, where if you remove, for example, if the attacker, the fab removes all these tunable delay buffers, then you will have race conditions and the chip's timing will fail, right? If you just arbitrarily select some random key values, then some of those key values will violate the longest path constraint, some of those key values will violate the shortest path constraints, right? So there is no like clear way of finding what the correct timing signature is going to be. The only way to do that is to redo the entire timing of the chip. So if you lock both the timing signature as well as the functional signature of the chip, then that presents a very formidable locking solution, at least at the module level. So this is actually being taped out right now by a chip that Northrop Grumman is producing with funding from Air Force. And we have come up with an entire design methodology that does this decision making as to decide where these tunable delay modules or tunable delay buffers should be distributed, and how should they be balanced with functional locking and all that wonderful stuff. Another significant component of at least processors is on-chip memory, right? About 70% of on-chip silicon is memory, register files, caches, what have you, mostly SRAMs, right? So instead of just locking the very little processor component or combinational component of your design, why don't we also come up with a method to lock memory, right? Now, memory locking is a more intricate approach. So we came up with a method to lock SRAMs, and we use this notion of delay locking here. So basically what we did was we came up with a method to distribute these tunable delay buffers in your SRAMs in such a way that the timing signature of, so SRAM is a very intricate module. It kind of sits on the boundary of analog and digital, right? So the timing signature of the SRAM module will be correct only when the key is correct, right? And when the key is not correct, then the timing will fail and the memory is not going to work correctly. So this type of memory locking was also investigated by us, and we came up with a design method to solve it. The critique of this approach is that, well, if you lock memory, then the attacker can always just replace on-chip memory with a timing correct on-chip memory, right? Because memory is just an IP that comes out of a memory compiler. So if you can just identify portions of your chip which has been locked, portions of the memory that have been locked, you can just kind of replace it with fresh memory modules, because everyone knows what the correct memory, and certainly the fab does, right? Now, the answer to that critique is that if 70% of your chip silicon is locked using this method, and if somebody has to replace 70% of your chip with this, then that's not a practical attack, really. They're not really going to do that. They may know what exactly memory does, but the chances of them taking the pains to go and reverse engineer and then replace and redo the entire layout with new 70% real estate that's really not a realistic thing at all. So I continue to feel that memory locking really has a very strong future. Um, so what's the effectiveness of memory locking? So what we did was that we once again use Obfusgem to lock some components of the cache tag, and we found that as you increase the number of keys, the percentage of runs with unrecoverable error grew very quickly. So memory locking is actually quite effective with very little overhead in that sense. So moving on. So let me just see if there are any questions, because I'm trying to okay, so nobody seems to have put anything in the chat, so I'll continue from here. Okay. I hope you all can still see my slides. Farinaz and Ramesh, just chime in if you can.
Yes, it's good.
Okay, great. Thank you. So now we come to the titular aspect of our tutorial, which is what about AI hardware, right? So let's ask this question in the context of design obfuscation, right? So we have this problem of obfuscation. And what we want to do is we want to lock the functionality or the timing or what have you, right? But what if the hardware is running an AI application, or what if it's a chip that does AI calculations like Google's TPU and what have you, right? Now AI or especially neural networks, they have a very different type of a computational signature. Fundamentally, these applications are resilient to small amounts of noise. That is just the way they are, right? I mean, they come within the general realm of approximate computing, and that's they are very resilient to noise, because that's just the way they are trained to be. So if the machine learning workloads are the ones that are of target to you, or if the hardware itself is machine learning hardware, then the obfuscation problem becomes very hard. Why? Because let's look at what happens when you run the SAT attack. When you run the SAT attack, then iteratively, as you reduce the key space, as you learn more and more about the correct key, even if you haven't found the correct key, if you randomly select any of the keys in the unknown space that you have found so far, the error rate in your module becomes less and less. So if you look at, for example, we locked a 16-bit fixed point adder or 16-bit fixed point multiplier, and we launched the SAT attack on it. So as the SAT attack iterations sort of continued, the baseline error rate in your functional modules became less and less. And after 5,000 iterations, even if the correct key was not found, the approximate key at this level was giving you an error rate of 0.012353%, which is basically zero. Now, for a conventional chip, for a conventional application, this may be not good enough in the sense that you want your hardware to be absolutely accurate. But if your workloads are machine learning workloads, then your application or your workloads can very easily train around it, or very easily not get too affected by such small amounts of error. So we ran a little simulation. So with the correct key, let's say MNIST, the accuracy was 99%, or SVHN, the accuracy was 93.51%. And for an approximate key found like this, the baseline accuracy was 92.64. So the difference between these two was very small, and that is now a hard problem, because how do you lock or obfuscate AI hardware when AI algorithms by definition are immune to small amounts of noise. So once again, this does require a deep architectural and system level investigation. And that is an open problem right now. And hopefully we will see some work from you all in the coming years to address this type of challenge. So now I have about 15 minutes, I would say, right? Because we started at 1:05. So in the remaining of this talk, what I'll talk about is how do you protect deep neural networks and other deep learning models from hardware-based attacks. So DNN is basically an IP. Training deep learning models comes at a significant cost, requires a lot of data, trained data, which only the big companies seem to have, high computational power, a lot of training, a lot of expertise in the engineers and scientists to train these models. So it's an expensive thing to build a deep learning model or a DNN model, right? But stealing these models is very, very easy. Several times the baseline deep learning model topology is what the attacker is really interested in. They are not interested in the values of the hyperparameters. They're not interested in the weights. They're more interested in just the topology, right? And that can very easily be stolen, as I'll illustrate later. And a lot of times the attacker may be able to train an approximate model based on whatever access they have to your model, and then refine it with new data that they may procure later, right? So the question that we are asking is, how do hardware-based attacks and defenses too, right, change the landscape of security in deep learning model? And that's what I'm going to talk about for about 15 or 13 more minutes. So last year's DAC, we presented what is called as the hardware protected neural network model. So the basic problem was as follows. You're a company like Amazon or Google or Microsoft or what have you, and you have spent an insane amount of time and energy and money training your deep learning model. You put that, let's say, in the public domain, or you share it with some folks, but you only want that model to run on authorized hardware. That's your objective, or to be used by authorized users. One way to do that is to encrypt the model, right? You'd use encryption, but imagine you have hundreds of millions of neurons, or let's say millions of neurons, if not hundreds of millions. And then you encrypt it, and the size of the model becomes just unwieldy, right? That's just too big, so you got to ship it, you got to store it, then you got to decrypt it, right? So yeah, that is a solution, but that's an expensive solution. So can we use hardware-based root of trust to have a lightweight obfuscation approach of these models, so that, yeah, you expose the models, let's say, in the public domain, but the models can only run on, hardware that has these keys preloaded and not on any other hardware. So one way to do that is, so we came up with this construction very simple construction, where we said, okay, you know what? Let's say the output of the MAC unit. So a neuron is just one MAC unit followed by an activation layer, fine. So what you want to do is the input to the activation function is inverted or not inverted based on a key value right here. That's it, very simple. It's just one small mux, right? So either you forward the MAC output as such, or the 2's complement of that MAC output based on this key. Now, let's say you know the authorized hardware, and you as the trainer know what that key is. So we came up with what is called as a key-dependent backpropagation algorithm to train this key into the weights themselves. So what you can do is then now modify the weights, and with very small, through training modifications of these weights, embed this key information in the weights themselves. Now, by exposing now this neural network in the public domain, those weights, the changes on those weights are going to be so small that an attacker will not be able to just figure out what the correct key is just by looking at the model or just by analyzing the model. But when you actually run this model on an unauthorized hardware, which does not have this little structure, right, that flips the output or not based on the key value, the error rate is in the model is going to be substantial, right? So we did that, and I mean, I'm trying to close this talk in 10 minutes, so I'll just skip this slide. So these are the results. So by using our key incorporated backpropagation algorithm, the baseline accuracies of these module, fashion MNIST, CFAR, SVHN was around this much, and this was very close to the non-key incorporated or non-key embedded backpropagation algorithm. But when these models were run on an unauthorized hardware which did not have the correct key, the drop in the accuracy was just like tremendous. It went down to like 10% or 9% accuracy, something ridiculously low like this. So something like this underscores the need for incorporating more and more hardware root of trust to build trustworthy artificial AI infrastructure. So another so one way to attack this could be that, okay, because the model itself is known in the public domain, what if the attacker can take this model and fine tune it to sort of make it work? And we have data to show that even if the attacker has as much as 10% of the original data set, the fine tuning attacks are not really going to work. Of course, if the attacker has the entire data set, then why are they even trying to steal your model? They'll just train their own, right? So a lot of times, we got to bring some amount of reasonableness into what the attacker is capable of doing, and that's what we did here. Okay, so this is the last thing that I really want to talk about, and then I'm going to end my presentation. And this is the reverse engineering attacks on. So what I presented in the previous set of slides was a protection coming from hardware, but now I'm going to present an attack coming from the hardware side, which is reverse engineering the DNNs themselves from cache timing side channel attacks. So what we did is we proposed what is called as Gangrene, which is you can call it a generative adversarial network based reverse engineering of DNNs. It's not exactly generative adversarial networks based attack, although it takes inspiration from there. It is a lot more optimization theoretic, but you can say that generative adversarial networks is just an optimization theoretic technique anyway. So fine. So forgive me for this little descriptor here. But anyway, so the basic idea is that, so what is the problem? The problem is that you have this very expensive neural model that is running, let's say, in the cloud, and then the cloud, so you're the victim, right? And let's say you have an attacker thread that begins to co-schedule itself on with you and tries to extract information about you or your model from the cache side channel approach, right? So I don't need to summarize what cache side channel attack is to this audience, but very, very quickly, what you do is you are the attacker. You preload your data into a shared cache and the last level cache, and then the victim runs its application, and then you run you read your data from the cache again, and the lines which are evicted correspond to the addresses in the main memory which the victim tried to access, and that gives you some information about the victim. So that's basically cache timing side channel attack, and there's an entire gamut of work on this, and I'm not going to summarize all that here. But the bottom line is that conventional cache timing or any side channel attack has targeted stealing the encryption key. Here the problem is easier because there is no notion of key. There is a deep neural network that is running on the processor, and you are trying to extract its topology. You cannot extract the weights themselves because this just tells you which addresses in the main memory was being accessed by the victim, and the sequence and the way in which these addresses were being accessed tells you something about the topological structure of the neural network. Topological structure of the neural network, and that in itself has a lot of information. So what Gangrene does is that it first extracts this cache timing signature of the victim, has all this data, and then it iteratively, using an optimization theoretic construction, tries to create layer by layer. This layer by layer approach is important, right? It tries to create the entire replicated victim's DNN by matching the cache timing signature. So what it does is that you have the victim's cache timing signature, and then one layer at a time, you try to create a deep neural network of your own, which matches this signature that you have. And there's a lot of theory that we investigate, and I'm not going to go into all that theory because I only have a few more minutes. But basically, the theory basically says that when the two converge, when the two timing signatures converge, then with high probability being the keyword here, the two DNNs have very similar layered structure. So here is some data. The cache channels cite traces of the victim as well as the attacker as the Gangrene is progressing is illustrated here. So for example, let's look at AlexNet. Fine. So AlexNet is this is the cache timing signature of the AlexNet over time, right? So this is just the way the peaks and the valleys are, and one layer at a time. So after the Gangrene has deciphered the first two layer topologies, this is sort of the dotted black line tells you the cache. The model that Gangrene figured out for the first two layers, its corresponding cache side channel structure, and then after first 5 layers, so you can see that layer by layer it is trying to match the original cache timing structure. And if you look at the paper, you'll see that for all these very sophisticated DNN models, we were able to extract precise topology for all of them. And that's a very powerful attack, right? So that does bring about the significance of asking the question as to, at least in the context of AI hardware, what type of AI algorithms and AI hardware, what type of defenses and attacks the hardware can pose, or the hardware can present. So anyway, we had another work called as neural Trojans. I'm going to skip that because that is not exactly in the context of hardware. And I'll summarize. So the overall summary is that there is a need for architectural research and design obfuscation. It is a very rich field. There are a lot of funding agencies, if you may, who are interested in funding this work, especially where I sit, which is 5 miles from Washington, D.C. In this neighborhood with all the defense industry and all the defense sector, there is a huge demand for this type of technology. Silicon Valley, perhaps not so much right now, because if you're thinking of building commodity class systems, then why do you need to protect that? But increasingly, even in Silicon Valley, this question is becoming very important because you don't want to expose your critical design details to your competitors, but certainly when it comes to government and military hardware, it's a very important problem. And then the AI models and the DNN models, they themselves comprise substantial amount of IP value, and security and integrity of these models is of primable significance. So hardware provides a unique vehicle both for attacks and defenses, and hopefully I've tried to whet your appetite for a new direction of thinking in hardware security and AI systems. So with that, I'm going to end my portion of this tutorial, and I thank you all for coming. And if there are any questions, I'll in the chat. I don't see any questions in the chat. Are there any questions I can answer right now? You may want to type it in the chat, or I don't know if there's a way to verbalize your question. If there is, then.
So for those of you, let me, if you don't have questions, the audience, I have questions for the audience, if that's okay. Right. So I'll quiz them on Ankur's excellent presentation. So a couple of questions I have for the audience. How do you see this technology, obfuscation, especially the framing that Ankur posed of Obfus Jam? What are there are a couple of things that Ankur presented there as, for example, which modules to obfuscate and so on. But from an architectural perspective, what are the interesting directions that you envision? One or two. I want to see how you could use this technology. So any responses would be good. Otherwise, I'll call out names then. The next thing I do that in my class too.
I'm going to invite my colleague and friend Amir Jalil to pose any questions. Amir, do you have any questions if you are tuned in? Okay, well, so like Ramesh said, I think the architecture community should look at, in my view, should look at this problem. And some of you may think that, well, we are protecting an architecture. The architecture in itself, the instruction set architecture is publicly known. It has to be publicly known. So what are we really protecting here, right? So these types of questions are important questions. So in the context of microarchitecture, what needs to be protected? What needs to be defended? I think that question needs to be asked first, right? The framework that I presented and you know that both Ramesh and Farinaz are perhaps bigger experts than I am, kind of tells you that firstly, this is a big problem right now, and second, there are solutions that logic can provide, right? But architecture and applications have their own kind of pressure mechanisms, right? So how do you kind of balance in the context of, let's say, microarchitecture? What's the right thing to protect? What is not the right thing to protect? Where is the actual information content clustered? So you can say that, well, the information content is in the controller, but the controller is so small that an exhaustive-based attack will unlock it, right? So what can you really protect, and is it even feasible to protect a microarchitecture in that context? So these types of questions are very, very important. They're fascinating questions.
So just to follow up on that, Ankur, there's one question from an anonymous attendee. Okay. How does the DNN model, without its weight values and without the training data, be valuable? Is there any particular example or use case for that?
Well, so I don't have a specific use case for that. I just wanted to present that you can actually steal the topology, right? Stealing the weights is harder because you can always encrypt the weights. And if that's what's going on, then stealing the weights in itself. But the topology itself has a lot of information, right? It tells you exactly how, so for example, it tells you what size of masks you used in the convolutional neural networks, and which layers were fully connected, which layers were not fully connected, how were you doing max pooling, and those types of things, right? Now, if you have that already, then with very little additional data, see, the assumption that the attacker does not have any training data is also incorrect, right? It has some training data. It doesn't probably have the same amount of training data that Google has, but it certainly has some training data, right? So a topology combined with some training data can actually be very, very formidable. Yeah. And trust me, if you go and tell Google that your topology itself can be stolen, but it's okay, your weights are not stolen, they're not going to like that answer, So the fact that you can steal the topology, in my humble opinion, is kind of a big deal, although I don't have a specific use case of that situation. Yeah. Hopefully I answered your question.
I think that's about.
Okay, so we are at 2 o'clock.
Yeah, go ahead.
Sorry, Ramesh, go ahead.
No, go ahead. Yeah.
So we are at 2 o'clock. So I'm going to invite my colleague and friend Farinaz to present. Farinaz, are you
Yeah, I'm here. Thank you so much, Ankur, for the great talk. I'm just going to take it and continue. I guess I have an hour like Ankur.
Yes, about 50 minutes, 55 minutes plus some Q&A. Yeah, sure.
Yeah. Okay, so let me share my screen.
So Farinaz, if you have more exciting material, you can take a little more of my time. So,
no, I'll not take this. I'll not take the spotlight from you, Ramesh. I actually would love to hear what you're doing because I haven't heard one of your talks for a while. So I'll try to be respectful. Okay.
Farinaz, trying to is the key word.
Correct. I'll try. Okay, cool. I just, I'm excited to be in front of the architecture community. As Ankur said, there's sometimes a little bit of a misalignment between the two communities that are indeed very close. So I'd like to take the opportunity to talk about some of the problems that I think, are really on the edge and, have exciting prospects. And hopefully there'll be more interest from the architecture community in address some of these problems. I don't need to tell you this. I guess by now this is old news that we're at the brink of the next industrial revolution, where automation enabled by the power of the AI algorithms, which is in turn really enabled by the amount of computing that we can do. As computer architecture actually enabled this computing at scale for us to do things that have never been possible before. But in turn, this new level of sophistication and complication in terms of the algorithms that we can develop are providing vast new opportunities and more than trillion million industry for us. And this is really taking much of the bandwidth of any industry you basically look into is going through transition. And a large part of this transition is really the power of these AI algorithms. And so far, a lot of these research has really focused on the functionality of deep learning, which is a rightful focus, right? If you're trying to run these huge amount of data and have complex algorithms that can deduct based on these huge data sets because they have the muscle to do this much computing, then functionality becomes a first-hand citizen, because at the end of the day, computing resources are really valuable for us. Of course, in the space of embedded and small devices, that's like definitely power limitations and other limitations come into play. But even in high performance computing systems, like the heat dissipation and a lot of things that are really near and dear to the hardware community and micro community would be really first-hand citizens. But they can do we achieve state-of-the-art accuracy, and these models are by themselves evolving. The deep learning is I guess the first generation. Then now a lot of problem domains are moving into transformer-based models. Newer model architectures are actually emerging as we speak. But the bottom line is that the challenges in the system, as I see it, is in integration of these deep learning algorithms into a bigger system. And I think, this is, I guess, Ankur was also talking about how, some of the challenges is really taking these point solutions that we have, for example, in hardware security community, and take it, to the system level, which I think, is more of a computer architecture problem. But, a lot of the problems, as I was mentioning in this area, have really focused on physical performance, where resource provisioning is limited. How do you take these computing giants and try to fit them into computing devices? How do you train them? How do you infer with them, and so on and so forth? The subject that I believe has to get more and more attention from the hardware community, and that's something that I'm going to discuss today a lot, is reliability or assurance. So these models are prone to attacks, and the attack, trying to mitigate these attacks takes resources. And how do you make the system such that these resources are, this is resource efficient and you can do some of these problems in real time in particular, is a huge challenge. There are other problems that arise. I'm not going to go through them in the tutorial today, but these are some of the other ones that I really think need attention. I think Ankur talked about some of the problems in hardware IP protection, but the AI systems, a lot of the algorithms are also considered IP, but also accelerators are considered IP. How do you take into account all this effort that has gone into designing these systems and make sure that it's not possible to steal things and replicate things is another big research topic. Last but not least, there's a lot of issues with data and privacy and preserving the user privacy that I believe arises with these models. I'm not going to have time today, of course, to discuss it. That's, I think, another big area of research where hardware can play a first-class citizen role. And that's a little bit less pronounced today. But with all that, I want to, just take one slide and talk about the approach that we've been taking in MIX, where the Center for Machine Intelligence, Computing, and Security that I've co-founded and co-directing at UCSD. So our view, and this is like an old view slide, like this is my slide since we started the center like 4 or 5 years ago, but this is, I think, really taking the gist of it, and that is, people who have been working on the data and algorithm side have always thought about that problems they're solving in a kind of software-centric way. And then what happened is that after they kind of optimized everything, they went and said, oh, how do I go and try to map it into hardware? And security was also often an afterthought. So after, they come up with data and algorithm, they try to kind of somehow link it with trusted platform module or other things into, some sort of a hardware, and then, kind of try to address these after the fact. The mixed approach that I've been trying to advocate is really taking this holistic approach where, where one considers all these aspects of data, algorithm, hardware, and security during the design, and instead of having point solutions, try to co-optimize this. And of course, you may come back to me and say, but this is not very scalable, because when people in hardware were completely separated from people in data and algorithm, then people in data and algorithm, they don't need to learn anything about hardware. They do their job, and then kind of this middleman came in the middle to try to map it. But that approach actually has problems because, efficiency is severely limited if we don't consider like the data and algorithms that we are trying to address, tangled with hardware. Either, we're designing new hardware, and this is something that is being done somehow in the accelerator domains that we have today, that people are considering what is the algorithm, so they try to design a custom accelerator. But that's, again, a little bit of a point solution, because there are many things that are coming up that don't have or don't get supported with that idea. And the answer to try to make this scalable and to avoid non-recurring engineering costs is really automation. So I think, this is the role of, where design automation and hardware architecture community can come together, because, the traditionally the field of automation and has been really strong in terms of how we are taking these huge functional systems and then we try to map them into a physical physical domain for the traditional designs. And now that the design is not just a description in a system Verilog, but it is a bigger description for going from algorithm and application all the way down. How do we take all these aspects into consideration, design new architectures, and come up with new ways how the algorithms can conform to existing architectures, but at the same time have this loop of automation going on and fit within the system. So with that, I just wanted to mention some of the ongoing work in my own lab, where we look into some of this robustness, efficiency, and real-time intelligence all together. I'll be talking about a couple of work that we've done in the past few years, where we looked into this integration, not just for the aspect of making the algorithms performant on devices, but for the purpose of making these algorithms robust. And in particular, I have some projects with the automotive industry, where real-time aspects of having a robust solution is a key for having these algorithms. For example, your car detecting various objects. If it's not in real time, this is not going to work. And if it's not robust, we will have catastrophic solutions that are going on. Other approaches that can, and we are looking into that. Actually, I just I'm leading a MIRI team on distributed control and interactive game, where we are trying the efficiency of these adaptive learnings and collaborative control and how they impact this whole integrity of the system, and how you could bring efficiency in to have a robust, efficient system that where the attacks are not just static, but the attacks are actually dynamic, and they have to work together. Of course, the problem of hardware security and complex optimizations in hardware is something that is near and dear to my heart. Ankur talked about some of the problems, like logic locking and design obfuscation, where has been initiated by my work and has been continued by several researchers throughout the years. But I really think there is a lot of room for applying some of these new algorithms in that domain to try to get better performance. And I'll be talking a little about that. As I said, I'm not going to be talking about multi-party security and privacy, which we are working on. But if you're interested in that, we actually have a paper coming up in CCS 2021, where we show the state of the art in the world in terms of how you could efficiently compute unencrypted data using provably secure algorithms out there. But the agenda for the rest of my talk today is how you make these ML models, and how do you make these models that are robust, but how do you make them robust with usage and co-design with hardware? Not just robustness. Like robustness is I think, probably maybe over address problem. In machine learning by now, people have been coming up with several robustness criteria, algorithms, really even proofs and this and that in that community. And I think what has been missing and what really needs a lot more research, and that research is actually housed in computer architecture and design automation community, is how do you design hardware for real-time machine learning robustness? And then this goes hand in hand with how can you make robust hardware And Ankur has been talking about some of the problems he has been leading, and in particular, I'm really impressed by the work he has done with JV in terms of the stat resiliency attack, and using the point functions for the logic for the combinational logic locking, which I was doing it for sequential, but that one I think is like a really great contribution. But again, a lot of these algorithms are still being evaluated, and in particular, a lot of attacks can be launched now that we have a lot more power at our disposal. We have machine learning algorithms that can really run fast and efficient. And how do you make this hardware more robust? By using the power of the machine learning algorithms to come up with new attacks and defenses that were not possible before. So that's kind of the second part of my talk. So first things first, let me go ahead and talk about robustness of machine learning algorithm, but actually talking about the roots of it as the hardware, I think should be a first-class citizen here. So I guess machine learning is everywhere where we look. This is all around us. And what has been pronounced and has made a lot of research effort mobilized is the fact that these machine learning models can make surprising errors. And these errors are, it turns out that, by making in particular, these errors have been really pronounced and worked on in the computer vision community, where it's easy to show examples, right? So you can add a little bit of a structured noise that is not visible to human eye, but that structured noise to the input that is added to the input actually makes the algorithm make drastic errors. And that's something that has of course, can hamper or tamper with the performance of these algorithms and make them make errors. And if these algorithms are used in automating real systems, then it is possible to make the system have errors and kind of make these very much possible. So the bottom line is deep learning models are not reliable. New attacks are being discovered every day. And there are two particular attacks that are being very much addressed by the research community. And one of them is the problem of the adversarial samples, which I just described. But the other problem, sorry. The other problem is the problem of neural Trojans, and that problem is a training phase problem. So as these models are getting trained, how do you make sure that someone is not inserting backdoors into your attack? Actually, people have shown it's possible to do so by adding poison data to the training algorithm. It is possible to make these algorithms have errors that are triggered by specific inputs. So during the execution, the specific trigger inputs are given to this to the machine learning model, and the machine learning model will either, if it's an untargeted attack, it will be kind of like denial of service. It would be just, making a random guess. If it's a targeted attack, it could, you could show it a picture of a cat, and you could direct this algorithm to say that this is a airplane, and still the algorithm looks correct when you're trying to develop it. So how do you avoid this type of problems? And as I was mentioning, there has been a lot of theoretical work, a lot of work in the by the machine learning community, by computer vision community, by many different communities and researchers in how to avoid these type of attacks. And of course, our work has been kind of one part of that. But I think what is unique is really trying to think about these algorithms like we were thinking about any other algorithm when you're trying to think about it as a computer engineer. What about efficiency? What happens if these algorithms are, some of these algorithms are fairly sophisticated, they can detect things, they can search the space of the model forever to try to come up with the holes and the defects in the model, but how do you actually scale things and how do you do efficient computing is something that is going to be the focus of my talk. So the first work that I'm going to talk about is actually rather old. We started this project in 2016 or 2017, and have got kind of got to just evolve the system. This appeared in ICCAD 2018, but what Deep Fence did was it was the first unsupervised defense, and I'm going to go through it kind of in more details. It also introduced the concept of AI explainability for adversarial defense for the first time in a practical way. I think, it has been and probably is the first ever hardware acceleration and real-time defense for adversarial examples. And this is a project that has actually gone full circle, has gone from, just being a concept and thinking about this in a broader way of thinking about system efficiency, but it has, we've been going, working with SRC and IARPA programs on adversarial defense for national security, for automotive security, and so on and so forth. And I think this is an approach that still has a lot of potential to get adopted and adapted for the various schemes. So let me just talk about the first aspect of this, that what made us think about unsupervised defense. And by unsupervised defense, what I mean is that all the work before we did Deep Fence have always thought about adversarial defense with respect to the attack. So they looked into what attacked the model, then they looked into retraining the model, and after seeing the attack, and then trying to see after seeing the attack, then making the attack more resilient, making the model more resilient against those type of attacks. And I kind of have a fundamental issue with that approach, because when you're building a machine learning model, you're capturing a huge dimensional space, which is the space of all possibilities of events that can occur, into a much less, in a much smaller size of a space. So, no matter how many parameters you're using when you're trying to train, say, a machine learning algorithm that can reliably detect people's faces, now you're mapping a huge dimensional space of possibilities into a lower dimensional space. And now these attacks occur because there are several things that you have missed from that huge dimensional space into this lower mapping of the space. And that is cause of a lot of errors that happens. And the way, if you try to fix the problem by trying to learn from the examples that don't pass your criteria, then what happens is that still, because the original space is huge, the space of possibilities of what you have not learned is so huge that, again, you will get into this cycle, into this vicious cycle, that there's always instances that you have not learned because you've mapped from a huge dimensional space into a much smaller space. It's not a one-to-one mapping. So instead, what we tried to do in Deep Fence was we tried to learn what is it that the current model knows, and can I use that to detect if a new sample comes, but that my existing model thinks that it doesn't know it. It may be, it may be just because I don't have a good model, but it could be that because it's an instance that I don't have enough assurance on. So I just, instead of saying, this is for sure an adversarial, the approach was, I don't know. So there are instances that, I learn from, and then if I can explain what is it that I've learned well, then if new instances come, if I haven't learned it well, I'm not going to be confident saying, I know this is a cat, because this may not be a cat because I have not learned it. Like, instead I say, this is an unsupervised way of learning what my model has learned. And then and by unsupervised, what I mean is not including a new attack. So if you try to introduce attack, you supervise learning of the attacks. I'm not trying to supervise learning of the attacks. I'm just trying to learn what the model knows. And this is where explainability comes in, because we wanted to know what is it that model knows, and so what are the things that this model tried to learn. But how could we do all this in during inference in a real time, so we can have an assurance satisfied. And this is a comparison with the earlier work that has been out there. It was the first unsupervised defense. It was robust against black box attacks, so meaning the attacks that don't know about the details of the model, the white box attack, where attackers know about the details of the models, but we try to also preserve the original architecture of the model. We did not try to come up with retraining of the model and see what happens. We try to just have the model there, and then checkpoints where check for the explainability of the original model, and then kind of adding all that in parallel to the original model, so we can have this parallel check. As the algorithm performs, we have these parallel checks that are parallelized in the hardware architecture, so they could checkpoint these algorithms at various points, but in real time, to tell us what is wrong with these algorithms. And let me, before I go forward, I think I'm maybe going too slow, but I'll try to speed up my tutorial for the rest of it. Is really in thinking about what do we understand about the adversarial subspaces. And the adversarial subspaces happen because of a few reasons. Let me just show you an example. Here I have two classes, a simple two-dimensional image, the light blue and the dark blue. And let's say I want to come up with a classifier that classifies these two classes. And if, for the sake of example, let's just assume that I'm limiting my class of classifiers to linear classifiers. And if I just have this linear class of classifiers, as you see here, this orange lines, all of them are valid classifiers for these two, for my simple toy example of two classes of data. And of course, depending on which of these boundaries I select as my ultimate classifier boundary, I will have a different error reported, or different distance between, based on the objective function that I have. And the non-robust decision boundaries that can happen in this example, as you see, of course, the orthogonal one is the most robust one, but this is like, just a toy example. In real life, we have a really complex structure of the underlying model. In particular, these adversarial examples happen because of the noisy data points and limited data in training, but of course, in inefficient use of regularization, where the regularizer does not really come up with the most robust boundary necessarily, where we are trying to address these problems. Now, I just want to talk a little bit about the concept. As I was mentioning, the black box AI models, like the ones we have in use today, these are, I think, subject to evolvement. What we are really going through is we are transitioning into what is being called by the XAI program by DoD, a third generation machine learning systems that can explain the rational, characterize their strengths and weaknesses, and convey understandings of future acts, and how you can make this interpretability, which is not a black box model anymore. It's interpretable and can tell us things about how it came up with its decisions, what it has learned. It's really something that I think has to come. So in the defense, what we did is we looked into the victim model. And then what we looked at is, okay, so, I have a, hardware platform, say I have a CPU platform or I have a GPU platform, but I have some resources that I can use for this defense. Now, where do I, and this is like, user defined, right? So this is not something that is defined by the algorithm itself, but I'm going to learn what this algorithm knows as it goes through its different layers about the distribution of this data. And if I can learn that in a few key layers, and I can run that understanding in parallel with the algorithm as it runs, then I can detect if things are wrong or things that are coming newly and I haven't seen because there's either noisy data or because my boundaries are not good enough. Then I understand, then I tell you, probably my boundaries are not good enough because I haven't seen a lot of data of this sort when I was training my algorithm, or not when I was training my algorithm, but when I was looking into the performance of my algorithm as the data was going through this network. And, because we are doing this checks in parallel, obviously, if you can do this parallel checks accelerated in parallel hardware, that would be the best. And that's what we did with the FPGA acceleration platform that we had for this problem. And it was like, 240 times faster compared to a highly optimized TensorFlow realization on embedded CPU GPUs. I'm sure a lot of people in the hardware community know how to do this, but I think the real meat here is trying to understand the algorithm and explaining it, and then trying to come up with a hardware architecture, either on CPU, GPU, or when you're trying to design a custom architecture that can make this algorithms efficient. So here, with my hat as a computer engineer, I'm looking into performance per watt as the first class citizen. And there was actually one more thing we learned when we looked into these algorithms from explainability point of view. And so what we learned was that, before we started this project, actually, when even now people are talking a lot about adversarial transferability. And what they mean by adversarial transferability is that there is actually data that gets transferred across different models. So if you train support vector machine versus, you're training a deep learning algorithm versus you're training a linear regression algorithm or any other clustering-based algorithm, the same examples that are adversarial for the deep learning are also adversarial for all these other problems. And they called it adversarial explainability. And that's something that I had fundamental problems with, and I still think is a misnomer, because when we tried to do this, and this is an example that we looked at in the MNIST benchmarks, is these samples that have been called adversarially transferable, these are actually samples that naturally are on the boundary for decision making, and therefore they're challenging for any machine learning algorithm that would try to model them. For example, on the MNIST dataset, which is a handwritten digit dataset, this was a 6, which was predicted to 1, and this is because it's a noisy data. Here is a 9 that has been mispredicted to 4. Again, even human eye may make that mistake, as you would see in this example. So I think, again, a lot of things could happen or could have different numeration or different side effects. But I think the fact that these data are getting transferred is not because this is fundamentally transferable data, because it's fundamentally noisy data. And this is something we realized after we tried to checkpoint the layers, and we realized these were like the samples that a lot of the attacks were coming up with, but these were the ones that the checkpoint was saying, oh, I haven't seen this example before. Oh, my boundaries for this example are really bad. So how can I say anything safely about this? Okay. So let me change gear. I want to talk about another project which we did more recently, and this is called Clean, where we looked into the problem of data poisoning attack. Again, with a hat of a computer engineer, how do you efficiently train models that are robust against data poisoning attack? And here, the attacker is embedding a black door inside the neural network. There's no impact on prediction accuracy on the clean data, but the high probability of predicting attack target class in the presence of the Trojan detect. So basically, here is a stop sign that gets correctly classified as a stop sign. Someone is putting a sticker here, and that's kind of the Trojan input. Now it gets in a targeted attack gets translated as a green light, and there has been again a lot of work on in this area. Looking into this from the standpoint of the view of the model inspection, reverse engineering the trigger, which is something actually we did in a deep inspect, which was our earlier work, trying to retrain the deep learning model to remove the backdoors, and so on and so forth. But in the Clean project, we looked into robustness, not just against simple triggers, but complex triggers, but again, looking to it from the perspective of explainability, and not trying to retrain the DNN to try to see what has caused all these backdoors, but looking into this from the standpoint of, if I have assurance in a few things that are clean, how could I make it such that my learning can become much more robust as I'm training things, and how could I do all these in an accelerated way so the power of my hardware accelerator is still in place, because as we have been working for the past years to try to improve the performance of these accelerators for either training the machine learning models that we have in our hands today, or to make the inference more efficient or more real time, and so on and so forth. So how do you make sure that you still are using those systems, still getting all those benefits, so we have still efficiency, but we can detect these kind of poisonous attacks. So data inspection type of approach, they're online defense, they work during inference, they determine if the input is infected, then they just try to discard it, and they require a lot of the training data and the labels, and have a really high computational complexity. Now in the CLEAN project, where we focused was, I don't want to get that complexity. What can I do? So we looked into less than 1% training data, no labels for the Trojan data required. Again, thinking about this as a model explainability, where things that are looking fishy to us are, just mark, oh, this is fishy. Because I don't know, I haven't seen enough of this. It doesn't fall within what I consider clean, but not thinking, oh, I know that my trigger looks like that sticker. So if I know my trigger looks like a sticker, let me just train an algorithm that tries to avoid that type of sticker. And then, of course, low computational complexity in terms of the high throughput and low power consumption. So it was, as I mentioned, it was an unsupervised defense. We were not using the Trojan samples or labels. The defense was established with a few clean examples. We looked into having mathematical bounds based on the assurance we were getting from the already trained model. And it was also the first accelerated defense for the data poisoning attack, looking into real-time execution. The threat model here has been that the client has access to model weights, but not to the training data. The client has access to a small subset of clean data, but they're not labeled. The client is unaware if the model is Trojaned or not, and we don't have a prior knowledge about the trigger shape and so on and so forth. Oops. So here, the methodology is, we have an objective function that is looking into capturing the data, statistics, or explainability of the data based on forming a parallel dictionary from the clean data. And this is like a common dictionary learning that I'm talking about. But what happens when the new data comes, we look into the dictionary that we formed, and we look into the distance between the data as it gets reconstructed. Does it fall within my dictionary, or it doesn't fall within my dictionary? And if it does not fall within my dictionary, it's something that I could not have explained before. So that's kind of the idea. But of course, forming a dictionary in real time was a kind of a challenge, because you could get a lot of resources for that. But we came up with an algorithm based on the sparse recovery, which works on both frequency and spatial domain, where this dictionary learning is completely parallelized with the main hardware. And then once we have this dictionary that is in parallel realized with the original design, what happens is that as the new samples come, as you're training your algorithm with an accelerator, this dictionary learning also works in parallel. It forms the dictionary, and then once you have less than 1% of the data that is randomly sampled in the dictionary, then there was a really good assurance in detecting the Trojan examples, in particular as you had these Trojans working in the field. trying to detect the samples. I'm kind of going, too long in my talk. I'm actually just half done with the first half of my talk. I need to really speed it up. We looked into how well we were detecting these Trojans. The scalability was really good, but we also could do, basically after we did this clean method, we could get a network where the attacks had a 0 success rate. So there's no attack success, and ground truth label, the recovery was mostly not reported in the earlier work, but we also reported that. We also did evaluation to adaptive attacks for this method, which was still more an adaptive attack means when you know what you're doing as a defense, so the attacker tries to redo their attack considering they know your defense, but still we were doing better in terms of the performance to the hardware attack. Well, anyway, so as I said, this was what I wanted to talk about in terms of how hardware can help machine learning algorithms get better performance in terms of robustness, not just in terms of like the performance of these algorithms as they run, but how you can think of robustness not as a standalone thing, but something that needs to get implemented in a real system and needs efficiency in hardware and system. Now, let's go back to the space where Ankur spent a lot of time on, and that is we want to make our hardware more robust. And there are these array of problems like, logic locking or obfuscation or other things that are getting a lot of attention. Can we improve the algorithms that are trying to attack or defend against these attacks by using the power of the AI algorithms? And that's something that is, I think, really an active, the subject of research. And, we'll talk about, just, as a sidetrack, I think, even, in the efficient hardware design, we are seeing a lot of machine learning helping the hardware design nowadays. For example, the pioneering work of my former student Azalia Mir Hosseini at Google Brain has shown that reinforcement learning can be used in unforeseen ways to act better, for the algorithms to act better, way better than traditional CAD algorithms in solving huge scale optimization problems. And this is just tip of what can be done in the space of the optimization. In fact, we just at UCSD with the leadership of my colleague Andrew Kong, we just got an NSF AI Institute where we are looking into how you could revolutionize some of these algorithms that are used in hardware design and hardware security by using the machine learning algorithms. So I'm not sure how much time I have to go through this, but I had a plan to talk about two work. One is machine learning based attack on hardware, which is trying to use genetic algorithm-based attack for logic unlocking, where you could try to train an algorithm that can perform a way better search for unlocking logic. And the other one, is I wanted to talk about is how we have used adaptive test pattern generation for using the machine learning algorithm for detecting the hardware Trojans. So this is a machine learning based attack on hardware. Ankur talked a lot about this, so I'm not going to have time to go through this. If you're interested, you can take a look at our GenUnlock work. So we looked into, again, parallelization and scalability of the key searching methods, and looking into this problem in a holistic way, to have the first algorithm, software, hardware co-design, and to devise efficient attack scheme. And it was encryption agnostic, in the sense that, it didn't matter which of the methods you use to do logic encryption. We tried to, we would be, this method would be learning that and would be attacking it with this efficiently. And, and we investigated this on a lot of benchmarks. Not going to be able to go through the details because I'm well over my time. This is another algorithm, for hardware Trojans, where, we use the machine learning algorithms for pattern generation for hardware Trojan detection. And it enabled the hardware Trojan detection with big performance trade-off. And so I guess my kind of few closing remarks is that I really think robustness goes both ways, that in order for us to design more efficient machine learning systems, we need the help from the hardware. And in order for us to design more efficient and robust hardware, we need to learn from the learning algorithms. So this is a field that has been largely unexplored, has a lot of potential to get explored. In particular, a lot of the things that are emerging are not for traditional learning systems like I was suggesting. There's a lot of movement towards the federated learning platforms, but even though the platform and the computing model is different, the main concept, I believe, remains the same, and that is co-optimization of the algorithms, hardware, and the protocols. As I mentioned, we have a lot of ongoing research in this domain. If you're interested in collaborating or discussing any of these, I'm always open for that discussion. But just to summarize, I'm really trying to advocate a hardware, software, algorithm, protocol co-design for robust machine learning and secure hardware. And I really believe we would not get where we want to get unless we think about end-to-end automated solutions that can address a variety of challenges in emerging intelligence devices and applications. With that, I thank my co-speakers and co-tutorial speakers, Ankur and Ramesh, for this for co-organizing this tutorial session. Would like to acknowledge the ACES lab members and the mixed collaborators who worked tirelessly on some of these problems. And if there's any questions, please take it up. Thank you.
So Farinas, there is one question that's typed up, and thank you for the great talk. So you may want to read that in the chat session.
Okay. Sorry, I didn't have time to look into the chat. It doesn't come up. Let me stop sharing. Maybe I can bring it up. Okay.
Maybe Ankur, you can read it out. So
it's a very long paragraph. So Farinas, can you see it in the chat?
I'm reading it. It's a long question. So let me. So the question is how hardware software-based mitigations like deepfence can contribute to fundamental AI security concerns like certified robustness. I think, even in certified robustness, if you're trying to certify the robustness, you will have some computing that goes on to do that certification. So if that is, that needs to run on a real machine and a real device, then performance and how fast you could do that certification becomes an important issue. This is not a hardware-based mitigation. I wouldn't call it a hardware-based mitigation. We actually have been doing all these mitigations in software. It's just that if you do this with hardware co-design, you make it much more efficient. So like, for example, deep fence is not just a hardware-based mitigation. You could do, we have done deep fence on a CPU, which is completely a software solution. It's just that, you know, if you want to get a good performance, and if you want to do this, and I believe even that implementation of deep fence is still way more efficient than many of the work that have not even thought about performance. So don't get me wrong that we cannot get performance unless we do co-design with hardware. But if you really care about performance, like, you know, I was telling you about the example of the automotive industry, where you cannot have anything that is not real time. You cannot wait for your certification to run for a minute before, you know, you have 2 accidents. Then hardware acceleration becomes an important issue and something that you want to take advantage of. It's not that, you know, it's only hardware-based acceleration that can help, of course not. But I think when you're thinking about mitigation, you need to think about algorithms that are efficiently run in the system. You cannot just think about algorithms in a, you know, even just you know, based on the computational complexity, like asymptotic complexity type of way. But I think, you know, these algorithms tend to be indeed very practical. These are not algorithms that have anyways like a lot of provable guarantees in terms of understanding how exactly you know, they're doing things, and that makes it easier for coming up with defenses from many aspects. But if you, I believe as a computer engineer, my main interest is to try to make these algorithms robust, but at the same time think about efficiency as they run in a real system. So the fundamentals, I think, you know, if you don't understand the fundamentals, you know, I guess, you know, the question is, how can you do this in using hardware community without understanding the fundamentals? I don't think you can do this without understanding the fundamentals. So I really advocate for people who are trying to do research in this domain. I think, you know, the task has become harder for the students as they go through, as things are getting more complex, but the students need to learn a lot more things in order to do fundamental deep research. If you want to do fundamental deep research that really contributes to learning and systems, it's not possible to do it without understanding the details of the algorithm and what it does to learn things. And I think there's no shortcut for that. I hope this answers your question. Any other questions, or I should give the floor to Ramesh? I tried to be on time.
That was perfect.
That was perfect, yes. So, yeah, Ramesh, do you want to take over? So we have a hard stop at 4, right?
Yeah, I'll make it sooner than 4, hopefully.
Yeah, but both of us have to be somewhere else at 4, you know, right? So.
Oh, really? Yeah, exactly. So anyway, hopefully you can see my screen. Good?
Yes, yes.
Okay, good. So I know I'm holding all of you back, but Zoom is a fantastic opportunity where you can just drop out. Having said that, thanks for joining us. And thanks for Ankur and the Farinaz and the micro team for having us here. I co-chair the NYU Center for Cybersecurity. The title of this presentation is High-Level Approaches to Hardware Cybersecurity. And reframing it, I see it as hardware being the new frontier in cybersecurity. If you have any questions, you can send me an email, or if you go to my website, you will even get my cell phone there. We can talk about that. You can call me anytime. So just to carbon date myself, circa 1991, I had a paper at Micro, at which point Micro was not as popular or as competitive. So just wanted to, so this is my dues that I paid to micro. Just want to give a heads up on that. So let me frame this problem of obfuscation at a different level beyond what Ankur talked about. So if you, at some point, high level, sometimes people call high level synthesis or ESL, it doesn't matter. It's a design methodology that directly translates high level C, C++ specifications into gates. HLS started, research started in the early 90s, and you saw my micro paper that was one of the not so popular HLS papers. However, it didn't take off until very recently as a commercial product for a variety of reasons. One, it was not yet ready for prime time because power, performance, and area metrics were not good enough. Logic synthesis was sufficient, and logic synthesis was effective in managing this power, performance, and area complexity of the designs. Fast forward circa 2012 or so and beyond, designing at this abstraction has become a prerequisite to manage complexity, and it has become also competitive in terms of the power, performance, and the area metrics. Further, it offers at least 4 benefits. You can envision many more. 1, it helps reduce the design time. 2, it helps manage the design complexity. 3, it helps reduce the verification effort, and you will see why. And it enables, as Farinaz pointed out, hardware, software, co-design, co-verification as well. How popular is it? 14 out of the top 20 semiconductor companies now use ESL tools. The typical application domains that benefit from HLS or ESL are communications, signal processing, computation, and crypto. Variety of CAD companies are supporting HLS. Mentor, Cadence, Intel, and Xilinx offer HLS tools. So in terms of productivity, we see HLS as a one tool. If you look at the graph here, the cumulative annual growth rate, CAGR, of gates per square centimeter is about 59–60%. At the same time, the CAGR of design productivity or the designer productivity is about 25%. And you see that, so that gap widening. By raising the abstraction level to C, C++, hopefully, HLS may allow bridging this gap. It allows maybe to support early design exploration. Just to reiterate some of these applications that significantly benefit from this productivity tool or productivity capability are image processing, video compression, vision, crypto, and ML as well. The video components in the Tegra chip, X1, I think, are designed using Catapult high-level synthesis tool. NVIDIA 4K processing was designed using C-based HLS. Qualcomm designs parts of the Snapdragon with the Catapult HLS tool. So there's a related trend that's going on as well if you are following what's happening in the IC design ecosystem. IC and system designs are increasingly using a lot of third-party IPs. For example, while there were about 16 blocks in a typical phone at the 90 nanometer node, at the 22 nanometer node, there are roughly about 200 IP blocks. So it's only going to grow more. So the increasing number of accelerators has its benefits. As I pointed out, there's this quick design time, trade-off integration versus design time. The benefit from specialist focus on accelerators and cores is immense. In fact, if you see the red line, shows that by 2024, 2025, about 90%, 95% of a design could be accelerators from third-party vendors, and the axis for the percentage of design on the left-hand side. The blue line right below that shows the cybersecurity investments, both actual and projected. And some of these investments could maybe dealing with securing these accelerators. Some of accelerators-based security, and we'll see what that means. So before I start discussing HLS-based security, I want to give you a quick background on high-level synthesis design flows. Here is a typical high-level synthesis design flow. A specification on the top left-hand side is translated into an intermediate representation called the control data flow graph. For those of you who are at the architecture level, you take your C code and you compile them into some such representation. This is what compilers do. They leverage state-of-the-art compilers. The most popular of them that you are aware of, that you probably are using, some of you, is GCC or LLVM. In the scheduling step of high-level synthesis, the operations in the control data flow graph, this is the middle picture in the top, are mapped to clock cycles. Some of them may take single cycle, like the adders. Others may take multiple cycles, 2 cycles, for example, for the multipliers here. One can get fast schedules that are possibly resource intensive, and one might have cost constrained schedules that have some timing overhead. In the binding step, again shown along on the same picture there, the scheduled operations in a clock cycle are bound to specific operators. For example, the multiplications are bound to multipliers. The additions are mapped to the adders. The variables or the edges are bound to registers, and so on and so forth. Data transfers spanning multiple clock boundaries bound to registers. Finally, you get a data path as shown below at the bottom, and the controller, which is shown on the right-hand side, and the implementation of the controller in the data path is shown in blue. Each state in the controller represents 1 clock cycle in the schedule. The controller sends control signals to execute operations on the specific operators in the specific clock cycles. Since operators and registers are reused, you see multiplexers in front of them in the data path in here. So in front of the multiplier 1 mapped on multiplication 1 mapped onto multiplier M3, you see a multiplexer in front of those. Similarly, the input to the register R1, you see a couple of a multiplexer as well. So you see, so the select signals of the multiplexers in this data path are typically controlled by the control. So with that background in a high-level synthesis flow, I want to highlight or bring in the importance, bring in security into the flow. Most hardware research has focused on, most hardware security research has focused on gate-level netlist and below that. Ankur has given an excellent introduction to the research in obfuscation, and most of it focused on gate-level netlist. Obviously, at this stage, when you're in the gate-level netlist, you lose important semantic information and are mostly left with structural information. So sometimes, especially for the designers who operate at the higher levels, typically the architects, typically the system designers, securing the right parts is hard. Security-aware HLS allows the designers to secure a design at the algorithm level. And let's see. So algorithm level security uses meaningful semantic information. For example, even somebody who is not security conscious, an engineer who is not security conscious, can easily identify and protect sensitive information at this high level. HLS and RTL, which stands for register transfer level, have semantic information such as sensitive constants, critical operations, protected control flow, runtime dependencies, and so on, while gate and layout level structural absorb this information and retain only the structural information. So what I'll do next is I'll present a couple of hardware-based high-level HLS-based hardware attacks and a couple of HLS-based defenses as well. Okay. So this is the high-level synthesis design flow. The question I want to ask here or the question I want to pose is, can electronic system level design or can high-level synthesis undermine security of the design that it generated? Before I do that and I show a couple of concrete attacks, I want to frame or highlight a couple of threats. The first threat is one of reverse engineering. Reverse engineering is quite a popular attack. Most of us do those. Here, an attacker tries to identify the device technology used in an integrated circuit, or an attacker might reverse engineer its functionality or reverse engineer the design. By reverse engineering, the attacker may find out regions where they can insert Trojans, or they can just pirate the design. Anyone in the downstream of IC or integrated circuit design flow can do reverse engineering. For example, the SoC integration house or the foundry or the end user, each of them could be a potential reverse engineer. Typically, the reverse engineer takes an IC, depackages it, delayers it, images those layers, stitches those layers together, annotates them, and analyzes the images and extracts the design. And sometimes it's called business intelligence, sometimes it's called IC teardowns, and you see that happening every time a new iPhone shows up on the market. There was a company called ChipWorks that used to perform reverse engineering. I think it's been acquired by some other company. I don't remember the new name of this company, but they do reverse engineering to detect IP piracy. That's one threat that's quite popular. A second threat is one of malicious third-party IP, third-party intellectual property. This is the threat model here is one of rogue 3P IP vendors. This could also subsume bugs that are potentially introduced in the IPs. Remember, this relates to the trend of IP-based design or accelerator-based design. Of course, one has to trust someone. We assume that you trust the SoC integrator. The SoC integrator procures all these IPs and potentially integrates them and sells them for their own profit. So you trust them. So that's one assumption that one could reasonably make. These Trojans could have a variety of effects. For example, the Trojans can cause wrong outputs. Furthermore, if the 3P IP modules are sourced from the same vendor, even if these are different modules, they can potentially collude. So it's not only a Trojan that is embedded in a single module, you could also have potentially distributed Trojans that span multiple modules. So these are a couple of threats. What I want to do is see how we can use high-level synthesis based approaches to thwart or some of these attacks. So let's consider HLS-based Trojan detection. I'll come back to HLS-based obfuscation or HLS-based reverse engineering prevention after this. For those of you who are in high-level synthesis, on the left-hand side, you have a very simple example that is typically used to explain some of the key concepts of high-level synthesis. Essentially, it's 4 steps. Simple specification. This is the classic differential equation benchmark, and a CD control data flow graph on the right-hand side. And this is a typical schedule. You also see the mapping. For example, in clock cycle 1, you see 2 multipliers and 1 adder. And for example, in the last clock cycle, you see only 1 adder, and so on. So the modules are potentially sourced from same IP vendor, an IP vendor, and potentially you don't trust the vendor, or potentially there are bugs in this one or more of these IPs. The objective here is then to generate a registered transfer level design for a trustworthy system that can detect Trojans, or that can mute the effect of the Trojans embedded in these sourced IPs. So that's the problem statement. So a little bit of a digression here. See how one can detect natural faults. And this has been well explored in high-level synthesis literature, but in general in design. The classical assumption for detecting natural faults is that at most one module is faulty. For example, here you assume that the module with shown on the left, O5 on the left-hand side, is faulty. Okay, and no other module is faulty. So the classical way of detecting natural faults is by duplication. You make a copy of the original schedule and binding on the left and map it, make a copy of them. So you duplicate the CDFG, you duplicate the data path, you map the duplicate copies to run on disjoint hardware. The checkers shown as purple detect output mismatches. The key assumption I want to reiterate is that at most one module is faulty. The overhead is a little over 100%, but this is classic detection, duplication-based detection. So let's see. Any questions on this? So the question then is, does this setup allow you to detect Trojans? So the question here is, does reliability ensure security? Let me stall a bit and see what people think. Is this a good enough architecture to detect Trojans in one of these modules? Let me pause a little. Yes, no? Ankur, any feedback from the community? I can't see it on my thing because I'm sharing the screen. Any answers? I can't see, so either Ankur or somebody else can see if there's any responses. Let me know, otherwise I will resume. Anyway, let me resume and let's look at, the question is, does reliability ensure security? And the security model here is one of a Trojan in a IP module. Okay. And to be very specific, the threat is one of malicious third-party IPs. The third-party IP vendor sells Trojan-infected IP modules. As I said, this could be just buggy IP as well. The SoC integrator typically uses the same IP module and makes multiple copies of those. Synthesizes using this 3P IP module. The Trojan is replicated, as you can see here, with those horns, every time the 3P IP module is reused. So duplicating and checking does not necessarily detect Trojans. Components with Trojans can produce the same malicious outputs. So the checkers cannot detect these malicious outputs. This is because, as you can guess, as you've seen from this figure here, straightforward duplication assumes that at most one single module is faulty. However, here all the modules are infected with Trojans because you use the same module multiple times, because you source one module from an IP vendor, license one module, and make multiple copies of those. So thus it violates this assumption of at most one module faulty. So reliability does not necessarily imply security, especially in the context of this security the threat. Okay, so what would you do next? What should we do next? So one thought here is to source the modules from different vendors. Here you assume that two vendors don't collude, which is a much more reasonable assumption than saying that multiple modules from the same vendor do not collude. So we call this vendor diversity. Assumption is that no two attackers or no two vendors collude. The checkers can detect now faulty and malicious outputs. The overhead, of course, increases. Although it's duplication, the duplication cost is the same, but now you have to source it from two different vendors. So the cost of sourcing almost doubles because you get the same module from two different vendors. Of course, there are additional costs of timing, similarity of implementation, and all of the other things. So since the designer now has to buy IPs from two different vendors, it involves 100% increase in the IP procurement cost, besides the power and area overheads. So now let's look at this concept of collusion, also known as distributed Trojans. Here is an example, wireless video capture SoC monitors. So here is an example where you have a camera watching the building entrance, and then somebody in the control room is monitoring that camera feed. And all of the things that you see in the middle are the various modules that are typically used to process this pathway. For example, in this video capture system, the CPU processes the camera output. It generates video frames. The crypto engine encrypts these frames. We use UART. You could use other protocols. You use UART to transmit these encrypted frames to the control room, and the frames are then decrypted and viewed. So this is a simple use case, and let's see what could happen. So let's look at this, what I call the parent-child collusion. Here, potentially, if the timer and the bus controller are procured from the same malicious vendor. In the normal operation, the bus controller controls the bus when the timer expires. During the malicious operation, the timer could send a trigger within its packet to the bus controller. The Trojan in the controller could potentially put the bus in the tri-state. The output of the SoC freezes, and the attacker sneaks into the building. And so this is all a scenario that I painted for you, but you could envision other more plausible scenarios as well. So the quick summary here is the timer or the parent module colluded with the bus controller, the child module, especially when they are procured from the same IP vendor. This situation occurs because the dependent operations are performed on the modules from the same vendor. Once again, the parent and the child operations are performed on the modules from the same vendor. Because of this poor design in terms of security, an attacker can launch this attack. So now you can imagine or see how one can thwart such an attack. So how do you, to reframe it, the question is, how do you prevent such collusions? To prevent such collusions, what you do is you map operations to diverse components. What I mean by diverse is components from different vendors. For example, you map the parent operation and the child operation to modules from 2 different vendors. On the right-hand side, I show you the vendors by 3 different colors. So to execute at least one of the parent operations on a module from a different operator, and this will immediately break this dependency of collusion. So now once you see this, you can then formulate it, develop an algorithmic way of operation to vendor mapping during high-level synthesis to prevent collusions and facilitate detection. So besides the parent-to-child collusion, there is also the parent-to-parent collusion. Here, what you want to do here is you map at least one parent on a component from a different vendor. So these are the various collusions that you could see. So what I have done here is I took some classic high-level synthesis benchmarks. I've shown you a few of them here. The second column shows the number of operations in each of these benchmarks. The third column shows the number of communication paths, which are the potential edges in the CDFG. And the number of operations is roughly the number of potentially untrustworthy IPs, especially if you map them all into the same IP, right? Similarly, the next column is the number of parent-to-child collusions, and we did analyze each of these designs and found out how many of them could potentially have parent-to-child collusions and how many of those parent-to-child collusions in each of these designs. And you see a lot of the possibilities. Similarly, there are these parent-to-parent collusions that I explained on the previous slides, a lot of them. So what this gives you is, if I'm an attacker, this presents me with the opportunities that to create malicious outputs. This presents me with the opportunities to collude. So what do we do then? So once we understand this additional complication of collusion, diversity, it simply doesn't work. So what you want to do here is duplicate and diversify, but also break these parent-to-child and parent-to-parent and other kinds of collusions. There's more work that has happened beyond. So this is a nice, colorful chart. Each color is a different vendor. And if you notice, vendors, these things naturally break collusions. I think this, and so on and so forth. And what you could do here is you can run this algorithmic heuristic algorithm, which is a node coloring algorithm that you can, during high-level synthesis, to do this during the binding step of high-level synthesis. So a quick pause here. What I've shown here is a potential threat model, which is not just simple Trojans, but complex and colluding Trojans or multi-module distributed Trojans. In high-level synthesis, during high-level synthesis, you can use this, and during especially the binding step, you can use the various constraints of parent-to-parent and parent-to-child collusions to break those possibilities for an attack. Okay, so that's about, I took about half an hour. Now what I'll do is go to the next part of the presentation, where I'll talk about reverse engineering. And this ties in with what Ankur started off with in terms of locking, obfuscation. More recently, there's a recent, a more fancier word being thrown around, which is called redaction, and so on and so forth. So let me frame this problem in this context here. So here is one way of looking at reverse engineering. Here, the attacker, we assume, is in the foundry. They have access to the GDS2 netlist. They do not have access to a functional IC. And the objective here is for the attacker to recover the design. Okay. And can you make it harder for the attacker to recover the designs? So if you look at this on the left-hand side, you see the typical flow. The left green part is where the designer is involved, and the orange part is where the foundry is involved. And once the foundry fabricates the chips, they give it back to the designer, and now the designer can verify, and then the designer can potentially activate this chip using the keys that Ankur mentioned. So logic locking typically happens after gate level synthesis. Once you have a gate level netlist, that's where you do RTL locking. Logic locking and gate level locking. What we propose is to do locking at a higher level, and you will see some of the benefits. Hopefully, I'll convince you with the potential benefits of doing that. I'll reiterate that as we go. And details of this are in that paper down there, but we have more recent papers as well. So for those of you well-versed in RTL or even high-level C code design and so on, some natural ways of obfuscation are as follows. Given an algorithm, what are the things that you can obfuscate, right? I see several ways of obfuscating an algorithm. I see at least 4 ways of obfuscating an algorithm. One is replace every constant or every sensitive constant with a register. Similarly, you could potentially obfuscate the control flow. Similarly, you could obfuscate the operations, and you can obfuscate the dependencies. And I hope you get the gist of the semantic information and the power of this obfuscation or the locking at the high level. You can immediately see the benefits. You can, as a designer, you can immediately point to things that you think are sensitive, and you can obfuscate it or redact it or lock it. So that's the benefit of operating, hopefully, at the algorithm level. So there, as I pointed out, we focused on the 4 ways of obfuscating the algorithm. So now let's look at obfuscating the control flow, one of those. The control flow, that is the branches in the specification, describe the evolution of the algorithm. The attacker can get insights on the algorithm based on the branch taken. What we propose to do here is to obfuscate these branches. The correct branch is taken only with the correct key. So if you have a wrong key, it's a wrong branch, and so on. So what you could do is just you can change it at focusing on the test. You can reorder the test. You can reorder the branches carefully so that you can ensure semantic equivalence, and on one hand, and confuse the attacker on the other. The key idea is that with code inspection, by simply inspecting the code, absent the key, no intel on which branch is real and which branch is false would not be possible. So that's how you can obfuscate using control flow, or you can obfuscate the control flow. Okay. So now let's look at obfuscating the operations. Here, the operations tell you what the algorithm does. If you can use the existing operations, or if you can add additional operations, or if you can create variants of operations, you can potentially camouflage the correct operation. For example, as I show here, you add mux, and you add a keyed mux, and you have the real operation on the left, which is the add, and you already have a subtract in the design, and you can, if you take that subtract output and multiplex in, or you see either a fake or a dummy operation, absent the key, you don't know which one is real and which one is fake. The correct operation result is propagated only with the correct key. Once again, I want to reiterate the ease with which a high-level designer can see the benefits of this. It's very semantically intuitive. Gate level net lists and layout level these obfuscations are that much more difficult. So let me go to the next kind of obfuscation. And these are, if you look at signal processing algorithms, the secret recipes in most of the signal processing algorithms come from the coefficients in the designs. So constant obfuscation suggests one to remove these coefficients from the circuit and store them in registers, or replace the constants in the design before they are synthesized, before they are submitted to logic synthesis from the design. This offers more protection. It, of course, results in less logic level optimization. It has increased area overhead, as you can guess, because you're eliminating optimization opportunities. You're replacing them with registers. So logic and netlist level obfuscations operate on the optimized logic synthesis, whereas if you take that away, you may not have some of these benefits of logic optimization efforts, which is power, performance, area metrics. As a designer, you know, some constants are not that interesting. Reset values, you may not want to obfuscate, but these are the, so once again, as a designer, you know what are sensitive coefficients that you want to obfuscate or redact. One other point I want to make is high level, the obfuscations at the high level can complement and supplement and coexist with the gate level and netlist level locking approaches. So one does not preclude the other. So the other thing that you could do is add additional dependencies. This is similar to operator obfuscation, but it's more operating at the dependencies, adding additional dependencies rather than adding additional operations into a mux. So once again, the correct paths are activated only with the correct key. And essentially what you may want to do is to create semantically different but plausible code variants. If these are implausible code variants, then again, an attacker or an attack tool like GenUnlock could potentially easily identify and eliminate. So of course, when you do these things, obfuscations, they may affect component latency, different schedules, different overheads, may have significant area overhead. So you can do a resource constrained obfuscation, extra operators, extra wires, extra muxes. And some of these can only be applied during high-level synthesis. And I want to highlight this point and see what the benefits of doing or the drawbacks of doing that. So this is the design flow I envision. You take a C++ specification, you do high-level synthesis. I identified many tools. Then you get, when you do obfuscation during high-level synthesis, at the end you get an RTL, which is obfuscated. I call this obfuscated RTL. And you also get a key, which is the design key or the locking key. Then This obfuscated RTL is compatible with all RTL synthesis tools. So that's good. And once you synthesize the RTL, you get obfuscated netlist. And on that obfuscated netlist, you can do all the locking techniques that Ankur highlighted or discussed in the first part of the tutorial. So at the high level, what HLS obfuscation lets you do is semantic obfuscation. Branches, dependencies, operations, and constants. And at the low level, gate level obfuscations lets you do structural obfuscation. So that's the difference between those two. Okay, so let's see what happens. Again, what we did was we used open source high-level synthesis tool, and I'll make a point on this. And this is a tool that starts with C and automatically generates an HTL. I have about 5 examples here. The second column is the overheads, the various amount of key material that I can procure when I applied these obfuscations. For example, when you do, there were 4 constants. Each constant gives about 128 bits. Together gives 128 bits. Similarly, 4 branches, they give you about 4 bits of key material. DFG variants, 88, they give you about 350 T. And if you add them all up, you get 484 bits of key. So at the bottom, as I said, you have obfuscated constants and the used key bits, obfuscated branches, number of basic blocks, and the associated key bits, total number of key bits. So as you can see, the generation of DFG variants is quite powerful. What it does, it combines dependency obfuscation, as I pointed out, as well as operation obfuscation. And the number of key bits is proportional to the number of basic blocks and not the number of operations like in the RTL. So the rest of the logic is generated using, can be automatically generated using the tool. So let me pause a little bit and point out some of the drawbacks of this. So what you need to do, so we used Bamboo open source HLS because I collaborated with an expert, the developer of this particular tool from Politecnico di Milano. Now, if I want to incorporate these constraints during high-level synthesis, for example, if I want to incorporate these constraints into the Mentor Graphics Catapult tool, or into the Xilinx Vivado tool, or into the Intel high-level synthesis tool, I have to, or BlueSpec and so on and so forth, I have to go and talk to each of these vendors. So incorporating them into each of those vendors' tools. So it's a heavy lift. So what we proposed as a compromise is something like this, right? So what we said is, look, instead of reaching out to each of these vendors and convincing them to change, open up their tool code base, or even convincing them to adopt our transformation into their tool base, we wanted to make it that much more easier for the designers to use these obfuscations. So what we propose is, let the HLS tools generate RTL, and then apply these obfuscations, or the 4 obfuscations on this RTL. All of a sudden, you do not need any vendor adoption. You can take this RTL, you can do RTL obfuscation, you can generate this obfuscated RTL, and you can generate the associated design key. We have done this. We generate a synthesizable Verilog, go through the synthesis flow, and you get an obfuscated netlist. And this is compatible with any RTL synthesis tool. And what we have done is, this is a tool that is, we call it Assure. So it's a Assure high-level synthesis tool. It's been, it's actively used by lots of defense contractors, by lots of companies, and a few other agencies and they're fabricating chips as we speak by incorporating these Assure HLS tool, which does not need any of the HLS tools to be opened up by the individual vendors of the HLS tools. So I know everybody is ready to move on beyond micro. So that's my message here. What you could see here is if you operate at the high level, you have this benefit, all the benefits of semantic level security. If you're interested on some of the other works that look at high-level synthesis and do the security assessment, add security during high-level synthesis, here are a few of the papers. And of course, there are many more papers, and a lot more work that's ongoing, and it's a very active area of research. And I hope for those of you who are in the architecture community, this is probably somewhere that's closest to where you see hardware or you interact with hardware. You could do, I pointed to high-level synthesis for Trojan detection. I did not talk about watermarking during high-level synthesis of the designs. I talked to you about obfuscation during high-level synthesis. I did not talk to you about taint propagation during high-level synthesis. I talked to you about HLS reverse engineering high-level synthesis-based designs. Or maybe I did not talk to you about high-level synthesis-based designs. That's a fascinating paper as well. Overall, HLS can be used for good and can also be used for bad. So in that context, and on that note, what I want to do is make a quick summary. High-level synthesis is probably a C-based design is becoming popular. So incorporating security at the C level, at the specification is maybe that much more easier, more intuitive, and can bring in all the benefits of the semantics that are still preserved at that level, like identifying the constants, identifying the, noticing interesting control flows, establishing additional dependencies, adding additional operations, or repurposing existing operations, and so on and so forth. And using your existing infrastructure like LLVM and so on, where you can morph your code, or upgrade your code, or change your code with all of these security constraints, is probably a good way to go. And on that note, what I've decided, what I thought is, I'm a little 4 minutes early. I'll not take up too much of your time. That's my phone number, and that's my email. And any questions, any comments, any thoughts? And thanks for your attention.
Thanks a lot, Farinaz and Ramesh. And I'd also like to thank the organizers of the micro conference and the tutorial selection committee. I know it's a lot of work. We also appreciate you all giving us the opportunity to present some of our ideas. They are non-conventional to an architecture audience, but the hope is that some of the things that we talked about today would motivate you into looking into some of these problems at a high level, application level, and architectural context. So the floor is open for any questions for Ramesh specifically, but all of us as well. We have a few minutes left. You can type your questions in the chat box. So we've had 3 questions which we have answered. Ramesh, if I may say some, if we want to use high-level synthesis for AI models, will the obfuscation approaches or some of the things that Farinaz talked about in terms of neural trojans, for example, will detection of those approaches look different, and if so, how? Because right now your entire or anyone as far as chip design is concerned assumes that functionality is a holy grail, which it is not when we talk about deep learning models. Functionality itself is fuzzy. So in that context, how do you envision high-level synthesis to evolve?
So if you just blindly apply the obfuscations that I mentioned, let's take the simplest obfuscation and the one that we explored a lot, which is the constant obfuscation. Just taking away all the constants from the implementation and replacing them with registers is a bad idea, right? Means it's an excellent
idea. In terms
idea
of overheads, you mean in terms of overheads?
In terms of yeah, so is a bad idea in terms of overhead, excellent idea in terms of obfuscation, because somebody can steal the IP, the foundry can get the IP. Again, we got to frame the problem carefully. You can steal the IP, but you don't get anything out of it because none of the constants are stored in there, right? But there could be a trade-off in between. On one extreme, take away all of the constants to some of the constants, and there you can do some analysis and find a sweet spot. Potentially there is something. I haven't looked into that. The other parts of this, like the dependencies and so on, that is to may mitigate some of the threats that you highlighted, where recovering the structure, right, could be done. But these are a couple of ways. I'm just focusing on the obfuscation aspects as well, but I'm not looking, I didn't, so those are the two problems I think could immediately fall into this framework. So in terms of neural Trojans, where you have at the specification level, put in some codes. So this is where one of the papers, I think bullet number 7 or so in one of the slides, shows that HLS can also help inserting neural Trojans. It's a good tool for the Trojan designers as well. Just like you design HLS for, you have HLS for ML applications, you can also have HLS repurposed for Trojans inserted into ML applications as well, where you can do all of these processes potentially. So those are a couple of things that come to mind.
Okay, we have a couple of more minutes, so last call, I guess, for questions.
So as you think of questions, or if you don't, I also want to chime in and reinforce what Ankur said. Thank you for having us, and thank you for joining us.
Well, there is one question by Satinder saying, is high-level synthesis generates unnecessary data path? I guess I don't understand the question. Ramesh, can you?
Yeah, so I can reframe. If you look at high-level synthesis, and the outputs that come out of it, not all modules are used in all cycles, even if you do full pipelining, iteration interval of 1, and so on and so forth. So in the sense of when they're not being used, the modules in a particular cycle, they could seem unnecessary. But you could, maybe I'm just reframing this according to my understanding. You can interrupt me, Satinder, at any point. So those unused modules can be repurposed either by an attacker for monitoring eavesdropping, or by a defender for defending.
Satinder, do you have any follow-up on that?
I think
Ramesh, you got the point correct. Thanks. Great.
Thank you.
Thank you, Satinder. Thank you for your question. Okay, we have 7 more minutes. So if you have another couple of questions, then feel free to chime in. If not, you know where to find us.
And we'll yield back your time, as the senators say in the US government, right?
Sure. I live in Washington, DC, so
I know.
it's appropriate. Okay. Well, if we have the permission of the organizers, then we would like to call an end to this tutorial.
Thanks a lot for your presentation. Have a nice day.
Thank you.
Thank you.
Thank you, everyone. Have a great weekend. Bye-bye.
Bye. See
Thank
you.
you. Bye-bye.
And thank you, Farinaz, and thank you,
Farinaz.
Ramesh, for all your wonderful knowledge
Yeah.
dissemination.
Talk
Bye.
to you in a few minutes.
Talk to you in a few minutes. Yes.
Yes.
Bye.
Bye-bye.